Okay, I was just going to go over a couple of the other tests that you can do for testing claims, hypothesis testing, usually called significance testing, sometimes called hypothesis testing. So we've had the situation where you test a claim about a population parameter. So let's say you had all the people in the town. What's their average height? That would be a population parameter for the entire population, their height, their average height for everyone in town. To test that, you wouldn't test everyone. You'd test a sample. You'd collect some sort of a randomized sample, a representative sample, hopefully. And you would take the average from your sample. And with the t-interval, you could estimate the population average height, or the average height for the entire population. With the t-test, you could test whether or not a claim about what the average height is for everyone in town, you could test a claim of that using your sample data to see if it seems likely or not that the claim is true, whether or not you can reject the claim, or if you don't have enough evidence to reject the claim. And again, if you don't have enough evidence to reject the claim, you would just say that you fail to reject it, that you don't well, you just fail to reject it. So you don't confirm an alternative, you just reject or fail to reject the default hypothesis. The default hypothesis is always that the claim is true, or if you're comparing, like I'll talk about now, if you're comparing two different groups, if those two groups are the same, that's the default assumption, that they're the same value for the average parameter. Okay, so we'll talk about different scenarios because you get different types of data. Sometimes your data is quantitative. So let's say we're talking about the height of people. That is a quantitative variable, which means that we can average it and we can talk about the average for everyone in the population, the average height. You could do average weight, average number of siblings, average score on an IQ test, anything like that. Those are quantitative variables. You could also have categorical variables, data. So like, what's your eye color? What's your favorite type of cuisine? What's your favorite genre of story? Is it sci-fi, fantasy, blah, 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 historical, counterfactual, things like that. Those are categorical. So you can't average those. You can only talk about what fraction of the people meet a certain condition. We call that what proportion of people meet a certain condition. So we've got some different tests depending on whether or not you have quantitative or categorical data. So when you're dealing with categorical data, we talk about the proportion of people. So the test you would use in your calculator would be the one proportion z-test, typically, with what we've looked at before. If it's quantitative, it would be the t-test or the z-test, usually the t-test, because you usually don't have population information. You usually just have your sample, so that would go with the t-test. That's the more common one for quantitative. Now we have a couple of other tests to talk about. Those are the chi-squared test, and there's two variants of that. And then there are the two-sample t-test, and there are two variants of that. So I guess there's four things to consider to add to what we already know. All right, so we'll go through those. The two-sample t-tests are a lot like the one-sample t-test. So with the t-test that we did before, we wanted to know, let's go with the average height. What's the average height of people in the town? Well, we're not going to test everybody. We're going to get a sample, and then we're going to find the average for our sample, x bar. We're going to find the standard deviation on our sample, That's S. And we'll know the sample size, how many people we sampled, N, lowercase n. And then we can put into our calculators with the t-test, what is the claimed average? And then the calculator will give us a p-value, which tells us the probability that we would get the data that we got from our sample, given that the claim is true. So assuming the claim is true, the probability of getting my sample data would be given by the p-value that I get from my calculator. If that p-value is high, that means that the claim is likely true. Or at least I have no statistically significant evidence of rejecting the claim. If the p-value is very low, let's say less than 5% or 1%, depending on what your confidence level is, or alternatively what your significance level is, your alpha value. If your p-value is so small that and therefore it's so improbable that you would have gotten your sample data given that the claim is true, that's reason for rejecting the claim. We always want to look at the p-value. And all of the tests that we're going to look at right now work the same way. You enter them into your calculator, you get a p-value, and then you decide whether or not that p-value is so small that you're going to reject the default assumption or the claim, or whether or not you don't have enough evidence to reject the default assumption. Okay, so I'm going to share my screen and go over a couple things, and then we'll go through how to perform these tests. Oops, that's not what I want to do. Present, blah, blah, blah. Okay, hopefully you can start to see my screen. Okay, so we have we'll start with the two sample t-test. Now, it could be a z-test I'm talking about if the standard deviation for the population, sigma, is known. But if you don't know that, if you only have S, or the standard deviation for your sample, then you'd go with the t-test. Now, there are two variants. I will start with the normal two-sample t-test. So before, when we had the one-sample t-test, there was this claim about where that's called mu naught, where the average value for the population was. Let's say the average height. Maybe the average height is claimed to be here on the number line. So my default assumption would be that the true average is equal to the claimed average. My alternative hypothesis could be that the true average is actually not equal to the claimed average. So we're going to see if we have reason to reject H naught, and therefore, or if we don't have enough evidence, we would not be able to reject. We would fail to reject H naught. But that's always the game. Do we reject or can we not reject? In that case, we're always, in any case, we're always checking out our p-value. Is p-value less than the significance level? So if our confidence level was 95%, our significance level is 5%. It's always complementary to the confidence level. So what we're doing is we're comparing the p-value to our significance level. So if the probability of our sample data is actually 5% or less, or actually I should say less than 5%, if we're at a 95% confidence level, that means alpha would be 5% or 0.05. If our p-value is less than 0.05, in that case, we would have reason to reject the default assumption because our sample data is so unlikely compared to the, given that the claim is true. But if our p-value is high enough, then our sample data is likely, or not completely unlikely, given that the default assumption is true or the claim is true. So if the p-value was above 5%, let's say it's like 0.8, 0.08, or even 0.8, 80%, then we could not reject H0. We would fail to reject. So we'd have to stick with the claim. We couldn't invalidate the claim. Okay, so with the two sample, we have two groups. So it could be boys and girls. It could be upperclassmen versus lowerclassmen. So like freshman, sophomore versus junior, senior. It could be people from town A versus people from town B. We have two groups of people. And instead of talking about, so our default assumption would be that the difference, I'll call it A and B, that the difference between the means is 0, that they're the same mean, that the mean from one group is the same as the mean from the other for the whole population, both populations. Kind of like they came from from populations that are equivalent. The alternative hypothesis would be that there is a difference between the means, that the difference is not 0. We're not really that close to 0. So that's the kind of thing that we're dealing with. Are these two groups the same? Do they have the same average value? Do boys score the same on this test as girls? That'd be how it goes. So it works the same way, only now you're going to have an X bar for one group and an X bar for the other group. You're going to have a standard deviation for one group, and you're going to have a standard deviation for the other group, and you're going to have a sample size for each of the groups. Now there is an option on your calculator called pooling. Do you want to pool the results? For me, for this class, I'm just going to say, just never do that. Just always say no. I don't think that should give you any problems on the questions that you have on the MyOpenMath. Pooling kind of just assumes that the standard deviations for the two groups are about the same. Maybe they are, maybe they aren't. We're not going to make that assumption. So I'm just going to say, just always don't worry about thinking about that too much. Just always go with no pooling. So in your calculator, choose no for pooling, but otherwise just enter in your information for the two groups and get your p-value and compare your p-value against the alpha. If the p-value is less than the alpha, you will reject the default assumption. Therefore, you would think that the two groups are different. If it's not less than the alpha, then you'd have no reason to reject the claim or the default assumption, which is that the two groups have no difference in their average value. So let's just go through how to enter that into your calculator. Sorry for the heater making a terrible ringing sound, if you can hear that. All right, so in order to do a two-sample t-test, the way, where you have two different groups, there's a couple of ways you could do that. If you have data for your two groups, you can just simply go to Stats, Edit, and put in data for the two lists here. So you could put in all the heights from boys and all the heights from girls, or scores on a test, whatever you got. You could put them in your two lists. If you don't have stats to work with, if you have data. So I'm going to go to Stat. Okay, so once you have your values listed in their list, you can go to Tests, and you can go to two-sample t-tests. And now if you were dealing with data, you would just say, list 1, list 2, frequency 1, frequency 2 is 1. Check to see if they're different, no pooling, and go. You just go off your data. But if you have statistics, if you're given stats, then you're going to have to put in your average value. Let's say boys scored 100 on this test. Their average deviation was 15. We had 35 boys. Let's say girls scored 110. Their average standard deviation was 18. There was, 32 girls. Let's see if they're any different. No pooling. Calculate. So according to that, with that many people, I got a p-value of 0.016. That's a less than 2% chance with 95% confidence, my alpha value, my significance level would be 0.05, and my p-value is less than that. So that means I have significant evidence to reject the default assumption, which is that there's no difference between the boys and girls. By rejecting that default assumption, I'm saying that there is a difference between the boys and girls, or at least I believe I have evidence to assume that. I should be right 95% of the time and wrong 5% of the time, given this method. So that's how you perform a two-sample t-test when you have two different groups. It's pretty straightforward. All right, so what's the other type of t-test that you could do? Well, there could be a two-sample t-test in which it's the same group of people. This is called so that was called an independent two-sample t-test when you have independent samples. When you have dependent samples, or what they sometimes call paired samples or paired data, is when you have the same student, Billy, Bobby, I don't know, Bruno, whatever, and you have test one, pre-test, post-test. So it's the same people, 81, 92, 78, 83, 64, 79. Let's say that we have our data. What can we do when we have the same person taking two different tests, or we have two different pieces of data from the same group of people, so that the two data are actually paired across the rows? They represent the same people. Well, what we're really going to do is we're going to take the difference between the values. So here we have a difference of 11 from later test minus the earlier test. I think 5, if I'm doing this right. Then, what is it, 15? So, I think that's right. No, that's, let's see, 6 to get to 70, then 9. Yeah, okay, 15. So those are my differences. So what I'm actually doing is I'm doing a regular t-test for the difference between the means. I shouldn't say the mean difference. So I'm not getting mean 1 and mean 2 and talking about the difference between the means. I'm not doing that. I'm taking the difference of each row and I'm comparing the mean difference versus 0 difference. So the question is not, is the difference between the means 0? That's not the default assumption. The default assumption in this case would be that the mean difference is 0. So, I don't know, it's a little different. Okay, so how would I put that into my tests? Well, I'm going to do different numbers, so I'm not going to keep these in mind. But if I go to my calculator in this case, typically I would have data, so I'd go to stats, edit. Let's put in, I don't know, 79, 81, 85. For my test 1, I'll put in 85, 91, and 99 or something like that. So my tests, they typically go up. Okay, so what am I going to do here? Well, I need the difference column. So I'm going to go up here and I'm going to type L2 minus L1. And I do that up in my level 3 or list 3 definition here, and I press enter. And now it'll do the subtraction for the entire list for me. Now I have a column of differences between the two other columns. So with that, with my differences, I'm going to go to stats. Now remember, this is paired two-sample t-tests. What I'm going to do is go to tests, and I'm going to do a regular t-test because I have one column. So I'm going to pretend like it's one set of data. For stats, well, actually, I'm going to go to data because I have a list. The claimed difference between the data will be 0 because I'm saying that the default assumption is that there's no change from test 1 to test 2. I'm going to have to put in L3 here, and there we go. So here I once again get my p-value. I get my test statistic. That is t is equal to 4.3. That means the difference between them is typically 4.33 standard deviations away. So they are quite separated, the two test values, versus the variation 4. We're usually more than 4 points away. So my p-value is less than 5%. So if I was at a 95% confidence interval or confidence level, I would say that my significance level is 0.05. And since my p-value is less than 0.05, that means I have significant evidence to reject the idea that the mean of the differences is 0. In fact, I think that the mean of the differences is positive, so the tests have gone up. So that's how you perform a t-test when they are paired, when you have the same person getting two values, one right after the other. And that's also how what we just went through previously, how you test if the two groups are different. So it's not the same person taking the same test twice. It's two different groups in each column. You would do the two sample t-tests in that case. Whereas if you have the same person doing something more than once, so you have data from the same person, so each row represents an individual subject in your study, you would do just a regular t-test, but you'd have to make a special column that was the differences of the values. Always you're getting your p-value and comparing that to your significance level. Same thing. All right, I'll probably just do that for this video, and then I'll do another one with the chi-squared test. So you can do the same thing with proportions, I should mention. So if I had proportions, I could go to a two prop z test. So I would just put in, okay, how many reds were in this bag of candies? Maybe 15. How many candies were there? 45. How many reds were in my other bag of candies? 25. How many candies were in that bag? Maybe 60. Is proportion 1 different than proportion 2? Let's see. Here my p-value is almost 40%. So that means the default assumption that the two are equal, have that same ratio of reds. That's what I got was so likely if that was true that I can't reject that claim. So I would go with the default assumption, which is that the proportion of reds in the one bag is the same as the proportion of reds in the other. So you could do that with proportions too. So if you have proportions, you would go with the two proportion z-test. If you have quantitative data, you're almost always going to go with the two sample t-test, unless you know the standard deviation for the population sigma. Usually you don't, but if you did, you'd do this one, the z-test. Usually if it's quantitative, you're going to go with the t-test. And if you have paired data, so it's the same person taking the test more than once, you do a regular t-test somewhere. Well, I guess that's up top. And use your difference column. So I hope that makes some sense. That's it for this one. I'll do another one on the chi-squared next.